Yeah, welcome back. So we'll continue our discussion on this mechanics and the dynamics of the wind turbine. So the last session, what we discussed about the uh, Euler beam equation. Okay, essentially the static beam equation or Euler-Bernoulli equation, and from this equation we have looked at one of the example, uh, which is cantilever beam with end load. Now we'll continue the same and look at other example of cantilever beam with constant loading. So we had this. So second example that we will look at it, cantilever beam with constant loading. Okay, so what we can draw the picture uh, for cantilever beam with constant loading. So let us have that. Let's say this is the beam, and you can have continuous loading. Okay, which is, let's say, load Q and Q of X. So this is X, Q of X is constant along beam. So what we have, Qx equals to Q constant, and EI is also constant. Okay, and so we can have this diagram. We can get this diagram once we find out the system. Okay, so let's keep that. So what we have here, Q by E dot I is d4 by dx4. Okay, so from here what we have, this Q by E dot I x4 by 24 c3x cube c2x square c1x plus c0. So this is what we get as a solution. Now we can put the boundary condition. So like we have at 0 0, which gets c0 equals to 0, and also we have d of is 0, that gets c1 equals to 0. So we will have m of x equals to d2w by dx2 e dot I. And where m at L is 0, d2w by L is 0. So what we get, Qx equals to dmx by dx, and Q of L, that means d3w by is 0. So let's say this is solution 2. Now what we can have, we can use these boundary conditions, and what we can write, let's say from equation 2, we can write x square by 2 plus 6 3x plus 2c2 at x equals to L equals to 0. We can write essentially, let's say 2, this is 3, this is 4. So this is from 3. From equation 4, we can write x plus 6 3 minus 1 by 6. Then from here, what we get, L square by 2 minus L square, we get 1 by 4 L square. So eventually we get it's q by ei x4 by 24 L by 6 x cube L square x square, which is q x square by ei x square minus 4lx, then mx equals to ei L square by 2, and we have qx equals to q into x minus L. So these are the solution for that. And if you now plot this is x equal to L and this is mx. This goes like that. And this is your q of x. So the curve would look like that. Okay. So this is how you have the this beam with constant loading you can have. Now we can see the maximum stress at boundary. Okay. So we had this so this is compression, this is tension, so this is max stresses at surface. This is 2D. Now, what you have, sigma is E into epsilon. Epsilon is small z d2w by dx2 mx I of x z equal to d sigma max ed mx eix. So that's gives you an idea about the maximum stress at the surfaces where it's getting active. Now we can see some I mean we can expect some numerical value. Let's say if sigma max equals to 250 MPa and d equals to 1 meter. So one can find out M max. What would be M max? So here, since d equals to 1 meter, you have I, which is pi by 4 d4, or I by d pi by 4 d cube. M max would be sigma max I by d. So that is 250 into pi by 4 into 1 cube. So effectively you get 2 into 10 to the power 8 Newton meter. So you can see a very high moment. So typically a higher moment will lead to plastic deformations. Okay, so that is what is going to happen. Now we can actually look at so what we can do. Look at the loads at blade. So we can look at the loads at blade root. Okay, so in clockwise direction. So typically for a blade in an ideal design, the distributed load, which is Q of R, is given by 1 by B, the thrust of the corresponding annulus. The thrust, the thrust of the corresponding annulus. Okay. So if we recall, let's say if this is the rotor hub and there is a blade like that, typically and this can be R and this is 2/3 of R. So essentially at this point, assuming all fast force is concentrated here. Okay. And B is number of blades, let's say 3. Okay. And this would be R, complete. That's the radius of the rotor blade. Okay. So what we have already have dF equals to 4A 1 minus A half rho U infinity square 2 pi R dr, so which is essentially this was corresponding to coefficient of thrust into A half rho U infinity square 2 pi R dr. That was equals to B into Q of R, and Q of R is half. So this already we have seen. Now what one can do, now the bending moment at the blade root, that is R equals to 0, can be found as m of 0, 0 to R, Q R, R dr. So what we can write, 1 by B CTA half rho U infinity square 2 pi 0 to R, R square dr. So this is R cube by 3. So what we have, 1 by B CTA half rho U infinity square into 2/3 pi R cube, 1 by B 2/3 R CTA of rho u infinity square. So this is essentially our F top total force on actuated disk. So this is total force on actuator disk. And similarly, what you can have the shear force at blade root is trivially found by U of 0 Ft by B. So one can think about that moment is m of 0 is Ft by B, which is total force on blade into 2/3 R, that is 2/3 of radius. That is what we get the moment. I mean, provided here the assumption that is there, that assuming all forces acting on 2/3 by R, and we get the right bending moment. I mean, one can illustrate with a simple example. Let's say and we have a blade like that at R0. So here you have Q0, here you have moment 0, and everything acting at, let's say, 2/3 by R, then Ft by 3 at 2/3 by R on each blade. Okay. So what you have, Ft equals to P by 1 minus A into U infinity. So let's say 1 meganewton or 6 megawatt at U infinity equals to 9 meter per second, and radius is 75 meter. Then what will happen is that m of 0 2/3 by R into, which is kind of 16 meganewton meter. Okay. So this is what the measure of the bending moment that you have. Okay. Now, similarly, one can say, let's say, what is the maximum bending stress at blade rotor? Obviously, you can, I mean, this is regarding the annulus cross section. So what we have, if you have a place R1, R2, and this is D equals to R2. This is your neutral axis. So here R2 my R1 equals to B, which is less than R2. So my moment of inertia pi by 4 R2 to the power 4 minus pi by 4 R1 to the power 4, which will be pi R2 cube B. So I by R2 squared into B. Then I have sigma max R2 by I M0, which is M0 by pi by R2. So essentially M0 pi R2 square into B. So let's say R2 equals to 1 meter, sigma max equals to 250 megapascal. Then one can say how thick should the blade root cell be. So one can kind of try to find out the thickness of the blade root. So I mean the one that we got that from here, straight away you can find out the thickness, which you can say m naught pi R2 square into 1 by sigma max. So if you put 5 mega Newton meter by 250 megapascal, 1 by 50 meter, around 2 centimeter. So you can easily estimate that the thickness of the root of the blade, how much it could be. I mean, obviously we have kind of seen that how along the radius these things changes. Okay, so root to half things would vary, and that kind of variation one has to bring into the design purposes. So these are simple talking about the basic structural analysis. These are again basic structural analysis, but one has to understand the complete picture about this basic structural analysis. And now what we would do, we would also look at the other part of the structural design and then connect back things with the aerodynamics forces like that. Okay, so we'll continue the discussion in the next session.